So in the last video we have done the load instruction designing of the single cycle processor, and in this video we will do the next instruction. Okay, the next instruction in our question was, if you see this question, the next instruction was this address, in this address location, that is in 0x1004. in this address location there is this instruction, guys, that is the store instruction. So this store instruction means what? The value in this register x6. So I have to take the data value which is present in this s6 and store it in the location, this location present in the memory. I have to write the data in the memory. Store means, so guys, store means what? The in this s6, the value which is present in s6, I have to write that data into this location present in our memory. So first of all we have to write the binary form and the machine language form. So what was the store's format? Do you guys remember? You told that there is immediate bits in store, but it is split. The first 7 bits is here, right? The first 7 bits are here. Then you have RS2 and RS1 values. 2 source registers are there. That is this, you have to understand that there are 2 source registers. That is, this is our RS1 and this was our RS2. So there is 2 source register. Then function 3 values are there. Then you have what? The opcode. Sorry, then immediate is split here. First 7 bit is here, then next 5 bit is here, then you have the opcode. So what is the format of this store? Is S type. Okay, so the store's format is this. Immediate is splitted, that is first 7 bit is here, then later 5 bit is here. Okay, then you have the RS2 and RS1 values here, function 3 values and opcode. For our instruction, the opcode for store is what? It was 0 1 0 0 0 1 1. This is the opcode for store. Okay, now for store it is SW. What would be the function 3 value of SW? We know SB is there, SH is there, SW is there. SB is 0 0 0. Okay, SH was 0 0 1. So SW is 0 1 0. So you got this function 3 value as 0 1 0. Now if you come to this question, if you see this question here, this is the immediate value is 8. Okay, so first 7 bit is here and later 8's value is what? 0 0 1. So 0 0 0 0 1 is 2. 0 0 0 2 raised to 2. Yeah, it's 8, right? So it is basically 0 0 0 1 4. This would give 4. Okay, 0 0 0 1 is our 8. Then since I want to write in 12 bit, it would be some more zeros we have to write, right? 7 8 9 10 12. This would be our this. In here, the first 7 bits, there's one more 0. Okay, first 7 bits, these are the first 7 bits. These first 7 bits are basically stored in here, and the later 5 bits are stored here. Okay, function 3 value already we got, opcode we already got. Now RS2 and RS1, this is what our RS1 value 9, which is given here in 5 bit format. S6 is our RS2 value in 5 bit. This much is done. Then you have to take group of 4 and find their respective hexadecimal values, right? Group of 4 and their respective hexadecimal values we will be basically finding, and that machine language we will get it here. These are all things we have already discussed previously, so I'm not going very depthly into that. Understood? So now we have what? Now we have our machine language. So if you see here, we will get our final machine language. This would be our final machine language, guys. So now let us understand here what happens in store. So store, I have already told you, in store, with the image itself I can easily explain to you that in store, first of all, what happened is that I have to find the S9 value, I have to add it with 8. This is the first thing that I have to do, and in that locations data I have to read. I have to read that data which is present in that location, right? And I have to write it. Then what I have to do is that I have to write that in our this location, that is the value which is present in S6. Okay, so that is, we have this S6 with you. I am passing S6 here, okay, and the value present in S6, let's just say 10. That 10 I have to write it in, I have to go to this WD, that is, this is a write data section where the data I have to write in the memory is present, and this is the address location. Now address in which, this is the address I have to write this data. The address is what? This 9, and 9 plus 8, this immediate extent would give us 8. 9 plus 8 would be this A, and in that A I have to write this data 10. So here mem write is 1. There is no reg write, we are not writing anything into register. In the load case we write the value into the register, so that why reg write was 1, but here no reg write. Understood? Now ALU control is 0 0 0 because we are adding. Okay, I hope you understood, because here what we are doing is that first of all we need to find the address of this. What is this 8S9? The value of this 8x9 we have to find. So for that I first pass the 9 bit in this A1, sorry, the 9's bits in this A1, and it will give the value which is present in 9, that is 0x2004 through this ALU's source A. ALU's source B is with this is immediate value. This is my immediate value. Now immediate values is split. So in the extender, what extender do is that it extends into this 32 bit, we know that, but here the immediate values split. If in S type and all, we know the immediate values are split, so immediate SRC would be 1. When immediate SRC is 1 means what? It will take all the splitted immediate bits and reassemble it into 1. That is why here immediate SRC is used. You can see before in the extender, when we learned the load, we didn't write the immediate SRC because the immediate is already present as a single in the single area itself. But here we know in S type our immediate is actually split into 2. That is, here also there is some bits, here also some bits. So if I put the immediate SRC to be 1, that means what? This splitted immediate values are reassembled together to get this 1, to get this together, to get the immediate togetherly. So that is why my immediate SRC 1. Now I am adding into this and I finally get this as the result, X200C. How I get S20C? If I want, I can help you with that. Maybe some hexadecimal addition is this, that is 0x you have 20004 is added with 10, right? So A is 10, B is A is 10, not added with 10, added with 8, right? We are adding it with 8. Let's see if what happens if I add it with 8. 8 plus 4 is what? 12, right? So 12, if you see, 12 is what in hexadecimal? A is 10, B is 11, C is 12. So you get here C. Now 002 is the addition. That is why you get 0x200C. The addition of 8 and the address in 9. Okay. Now in that address I have to write the value which is present in S6. So now next step is what? I have to pass S6 bits. I have to pass S6 bits here. Now in the A3, what I did, in the A3 I am passing this S6 bit, that is let us say A2. In the A2 we can pass, okay, anywhere you can pass, that is actually 24:20 is the bit. And in that S6 I am RD2 would give what? S6. In S6 I pass this 6 and RD2 would give us the value in S6, that is 10, and that 10 I am passing to WD. What does WD in data memory means? WD contains a data that you have to write into the memory at the location of A. A is this location which we already got as this. So in that location I enable the write enable to be 1. So that means WD's value becomes this, and all this read data and all was the previous ones, that is load. Now we are not caring about this, only this is actually some parts are of the load in here, but now we have to focus only in the part where store comes. Here our in this address we have write this, mem write becomes 1. Understood? So this is what store actually, how store works. So now you also have understood how immediate SRC is 1. Immediate SRC is 1 in order to make sure that the in store the immediate values are split. So you need to write it as 1. That is why my immediate SRC value is basically 1 here. Now guys, so S type is a specific RISC-V instruction format, unlike R type or I type. The immediate offset is split into two parts. We know they are split into two types. So this is the key design queue of RISC-V that keeps register. Now that's not needed. Now the base address, first of all, sign extended we have understood, we have used this 8 sign extended is used, and then base register plus sign extended would give us the memory address in which you have to write the data to. Now S type, the data is split, so we have to reassemble them using this extender. The extender reassemble them into this 12-bit. That is why we use the extender here. Understood? So that is what the instructions complete path is. Now here there is no reg write, here only mem write is there. We are writing into the memory, no, we are not writing into the register. So these are the difference here. In load type, from the memory's value you are writing into the register, but in store the register value you are writing into the memory. So that means here no mem write, but here mem write is there, but here register write is there, but here no register write is there. This is the important thing that you have to understand. When the register is the, this is a complete flow. You understood here PC, this is the address that the PC has. So the PC, when it gives to the instruction memory, it gives this final machine language in the store. Now X9's value is this 0x004, which is given by the registers, and S6 value is 10. Now the extent, what does it do is that it will add this 0x2004 with the immediate value, and you get this address. In this address you are storing the value of this 10 here. Now again you are updating our address. Later you get, now you will again update our address, and next instruction would be 0x1008. Next you have to understand what would be the value in 0x1008. Fine. Now there is ALU SRC. ALU SRC is 1 only in the case of load and store, because when is ALU SRC is 1? ALU SRC is not given in this diagram, but there is one data, one control which is ALU SRC, and ALU SRC's value would be 0 in other cases, but in load and store the ALU SRC value is 1, because in source B the immediate value is coming. Whenever in the source B the immediate value is coming, then ALU SRC's value is 1. That you have to understand. Otherwise, that is, if normal addition subtraction between registers and all, it is 0 0 itself. Okay. Now for add, the ALU control value was this ALU control, we have added the value, so it is 0 0 0. But for subtraction it is 0 0 1. For subtraction is the AND is the, OR is the, SLT is the. So for these are the different values for different case. For load and store, it is always 0 0 0 0 0 0, which we have already seen here, right? But for if it's between registers and all, if you're adding and all, what happens? Then it is add is 0 0 0, subtraction is 0 0 1, and is 0 1 0, or is 0 1 1, and shift left logic is 1 0 1. Fine. This much we have understood. You have understood how ALU SRC is 1, when immediate SRC is 1. When is immediate SRC is 1? Immediate SRC is 1 in S type when you have to, when the splitted immediate values you have to combine to one single value, then the immediate SRC is 1. Yeah, this is for the store. Next we will do the next instruction. Thank you.